Good morning. We continue with the basicity of aromatic amines. In a broad generalization, we can say that electron donating group will increase the electron density on the nitrogen atom of aromatic amines. Therefore, electron donating group when attached to aromatic amines, that substituted aromatic amine will be more basic than our aniline. That means, so this we have discussed in the last class. Here it is NH2 group, and suppose here it is electron donating group EDG. Electron donating group is attached to the ring. This electron donating group will increase the electron density on the nitrogen atom. Therefore, this will be more basic than our aniline. Okay, NH2. Okay, this is the first point. So, first reason, EDG will increase the electron density on the nitrogen atom. EDG will increase the electron density on the nitrogen atom. Second reason, this EDG attached group on protonation, so you can see that H plus, since this can easily take this H plus and we get protonated amine NH3 plus. Okay, here it is EDG. This second reason, this protonated amine it will be stabilized by EDG. This EDG will stabilize this protonated amine. Okay, these are the two reasons. You can see that EDG attached aromatic amine is more basic than our normal aniline. Second point we have studied. Second one, when electron withdrawing group, okay, NH2 group, if electron withdrawing group EWG, electron withdrawing group, what will happen? Will decrease the electron density on the nitrogen atom, and therefore which will be less basic than our aniline, because this electron withdrawing group will withdraw the electron density from the nitrogen atom, or will decrease the electron density on the nitrogen atom. Therefore, it will be less basic than our aniline. Okay, this is the very broad generalization of aromatic amines when there is a EDG or EWG is attached. Okay, now let us come to another important point, that is ortho effect. Ortho effect. Okay, ortho effect. What do you mean by ortho effect? We can see that ortho substituted aniline is less basic than our aniline, irrespective of the electron donating or electron withdrawing group attached, or irrespective of the electron donating or electron withdrawing nature of the substituent. What is that? This is important. Ortho effect. Ortho substituted aniline is less basic than aniline, irrespective of the electron donating or electron withdrawing nature of the substituent. That means, look at it here, ortho substituted aniline. Okay, here it is NH2 aniline, ortho substituted aniline. Suppose here it is EDG, electron donating group. In a broad generalization, we said if there is electron donating group which will be more basic than our aniline, that is the point just we have studied. But here we are studying another important point, ortho effect. Suppose if the electron donating group is at the ortho position, then what is happening? If the substituent is at the ortho position, then this will be less basic than our aniline. Okay, and similarly, if whether it is irrespective of here it is electron withdrawing group EWG, whether it is electron donating group or electron withdrawing group, irrespective of the nature of the substituent, this is always less basic than aniline. This is what is called ortho effect. What is that? Ortho substituted aniline is less basic than aniline. This is ortho substituted aniline. Here it is the substituent is electron donating group, and in the second it is electron withdrawing group. Irrespective of electron donating or electron withdrawing nature of the substituent, this ortho substituted aniline is always less basic than our normal aniline. Okay, this is what is called ortho effect. Okay, the reason could be, you can see that the close proximity of these two groups, these two groups are very close, therefore steric factor is there, electronic factor is there. Because of these factors, what is that, ortho substituted aniline is always less basic than aniline. There are two factors, one is steric factor and the other second one is electronic factor. Because of the close proximity of these two groups, because these two groups are very close, therefore steric factor is there, electronic factor is there. Because of these factors, we can see that ortho substituted aniline is always less basic than aniline. This is what is called ortho effect. Now look at here. When you consider ortho substituted, meta substituted and para substituted aniline, what is the order of basicity? You have ortho substituted NH2. Okay, here is also NH2. Okay, this is what is NH2 is electron donating group NH2. Okay, this is EDG. Okay, this is ortho substituted, and again one more NH2. Suppose here it is the NH2 group is the meta position, and the last one here NH2, and here is also NH2. This is at the para position. Okay, now this is EDG. Okay, electron donating group. So electron donating group is at the, here electron donating group is at the ortho position. NH2 group is electron donating, another NH2, one more NH2. This is at the meta position, electron donating group EDG. Here EDG at the para position. When you consider the basicity of these three substituted aniline, okay, you can see that the least basic is as we have discussed, when it is EDG is at the ortho position, this is least basic. Then what is that, meta substituted aniline, and the most basic is para substituted aniline. This is the order of basicity. The least basic is ortho substituted, then meta substituted, and then para substituted if the group is EDG, electron donating group. Okay. This we can explain, as we have explained EDG, when it is ortho position, it is seen that this is least basic because of electronic repulsion, steric factor, etc. Now we consider why para is more basic than meta. We can see that least basic is ortho, then meta, and then para. Why para is more basic than meta? We consider another example. Okay, here look at it here. here it is NH2, and here you can see that OCH3. This is also electron donating group. OCH3 is electron donating group. Okay, EDG. This is EDG. You can see that this is less basic than, or you can see that okay, NH2. Okay, this para. This is OCH3. Here it is para. This is more basic. Okay, so para, this is electron donating group is at the para position. When the electron donating group is at the para position, it is more basic than meta position when it is at the meta position. What is the reason? Look at here. You can see that this is very important point. You can see that this OCH3 is electron donating effect. That means it has electron pushing effect. OCH3 is electron pushing effect because of the, look at it here, electron pushing group. That means electron donating group. Okay, this way. Okay, due to the presence of lone pair electron, this way. This is electron pushing effect. That means it has a plus M effect. It has plus M effect is there. Electron pushing effect plus M effect. Because of the electron pushing effect, what will happen? It will increase the electron density on the nitrogen atom. It will increase at the same time. This OCH3 group is it has a minus I effect also, because see, you can see that OCH3 group is electron withdrawing group. It has a minus I effect. Okay, so here it is a plus M effect is there. Similarly, minus I effect also there. Okay. So once again I am explaining. OCH3 group is having, because of the lone pair electron, it is having plus M effect. Okay, that means electron pushing effect is there. Okay, it will undergo resonance. Resonance is there. That means plus M effect or plus R effect is there. Because of this resonance. Plus M effect or plus R effect is there. At the same time, OCH3 group has electron withdrawing effect. That means minus I effect. It has a minus I effect. But here you can see that plus M effect or plus R effect outweighs the minus I effect. That means, or you can see that the plus M effect is more prominent than minus I effect, or plus M effect is more prominent factor in the case than minus I effect. That means because of plus M effect, the electron density is increasing. Okay. Now, why plus M effect or R M effect outweighs minus I effect? Why it is how it is outweighing minus I effect? Let us see why plus M effect is more predominant than minus I effect. Look at it here. See, look at it here. Why plus M effect is important than minus I effect, or plus M effect, how plus M effect outweighs minus I effect. Look at it here. First I take the para position. Okay, look at it here. Why NH2? Okay, NH2. Sorry, not NH2, OCH3. Here it is NH2. Okay, NH2. Look at it here. Okay. This pair of electron is going here. Plus M effect I am explaining. Then this pair of electron is coming to this carbon. So we get a structure like this. Okay, here it is double bond OCH3. Here it is plus, and here it is negative charge. Here it is like this, and here it is NH2. And this pair of electron is coming here. Then this pair of electron is moving to this carbon. Okay, then you get a structure like this. Look at it here. Okay, here it is double bond OCH3. here it will become double bond, and here it is NH2, and here it is a minus charge. Okay, this pair of electron is moving, minus charge is a pair of electron. Okay, now in the next structure, this pair of electron is coming here, then this bond is shifting to this carbon. Okay, so you get a structure like this. Here it is like this, here it is a bond, and here it is NH2, and here it is a pair of electron with a negative charge, and it is OCH3, of course a positive charge. Next step, this will come here, and this bond is going back, and we get a structure like this. Okay, here it is NH2, okay, here is NH2, okay, here it is a bond, and here it is OCH3. Okay, the positive charge is removed. Now you will get here 1, 2, 3. The third structure, this is first structure, first resonance structure, second, and in the third resonance structure here, this is very important. The third resonance structure, you can see that when you look at the third resonance structure, you can see that a negative charge is present on the carbon to which the NH2 group is attached. So NH2 group attached carbon is carrying a negative charge. In the structure 3, you can see that the NH2 group attached carbon is carrying a negative charge, and hence this negative charge on this carbon will increase the electron density on the nitrogen atom, and hence the basicity will increase. Once again, we can see that when the electron donating group is at the para position, it is more basic than when the electron donating group is at the meta position. The reason is that when the electron donating group is at the para position, the plus M effect, because of the plus R effect or resonance effect, you can see that the NH2 attached carbon is carrying a negative charge. That negative charge will increase the electron density on the nitrogen atom, and hence this aniline is more basic. Now, such a situation is not present in when the electron donating group is at the meta position. Now, when the electron donating group OCH3 is at the meta position, look at it here. When it is at the meta position, this carbon, that means NH2 group attached carbon, will not get a negative charge, and hence it is less basic. So, okay, now let us take when it is at the, let us consider when OCH3 group at the meta position. Look at here. NH2 OCH3. Okay, OCH3. Now look at here. This pair of electron is shifting to here. Then this bond is shifting to this carbon. Correct? So you get a structure like this. Okay, here it is like this. Here it is like this. And here it is double bond OCH3. Oxygen is getting a positive charge, and here is a pair of electron. Of course, NH2 is here. Okay, and in the next step, what is happening? This pair of electron will be shifted to here. Okay, then what will happen? This bond is shifting to here. So we get a structure like this: double bond OCH3 plus, and here is double bond, and here is a pair of electron, and here it is NH2, and it will continue like that. It will continue. Okay, here it is a double bond, so this will come here, and okay, that you can complete. Now you can see that here when OCH3 group is at the meta position, there is no possibility of getting a negative charge on this carbon. That means NH2 group attached carbon will not get a negative charge. Therefore, but when it is at the para position, NH2 group attached carbon is getting a negative charge. That negative charge will increase the negative charge on the nitrogen. Therefore, para isomer is more basic than meta. Clear? Okay. Similarly, one more factor we explain. Now, electron withdrawing group. When the electron withdrawing group is at the para position, electron donating group at the para position, which will be more basic than electron donating group at the meta position. Now, electron donating group at the para position, you can see that electron donating group, suppose NO2 group, if this is NO2 group is electron withdrawing group, electron withdrawing, that you know. When the electron withdrawing group is at the para position, it is less basic than when the electron withdrawing group is at the meta position. Reverse, opposite of electron donating group. When the electron withdrawing group is at the para position, which will be less basic than when the electron withdrawing group is at the meta position. Okay, but in the case of electron donating group, what was that? When the electron donating group is at the para position, what is that? Which will be more basic than electron donating group at the meta position. But in the case of electron withdrawing group, when the electron withdrawing group is at the para position, which will be less basic than when the electron withdrawing group is at the meta position. What is the reason? Look at it here. Okay, look at it here. What is the reason? NH2. Here it is NO2. Okay, NO2. Electron withdrawing group. Okay. Now look at it here. Okay. Okay, NH2, electron withdrawing group. So now look at it here. This pair of electron is shifting to here, correct? Now you can see that this bond is breaking from here. This bond breaks from here. So you get a structure like this. Here it is double bond NH2. Okay, and okay, here it is like this. Okay, here it is N double bond O, and okay. Okay, N double bond O, here it is O, okay, like this. And in the next position, next stage, this will be shifted to here. And you can see that, okay, this bond is shifting to this carbon. Correct. So we get, now look at it here, we get a structure like this. Here it is, will become double bond. Okay, when it is shifted, here it will become positive charge. Double bond NH2, here it is positive charge, and here it is a negative charge, N double bond O minus, and here is a bond, and in the next stage this pair of electron will be shifted to here. This double bond is shifting to oxygen, and you get a structure like this. Okay, here it is like this, double bond NH2 plus, and here it is double bond, here it is O minus, and here it is O minus. Okay, now in the next stage you can see that okay, this pair of electron again will come back. This bond is going here, and this is coming here. Okay, so what do we get? We get a structure like this. Okay, here it is like this. Here it is double bond NH2 plus, and here it is a negative charge, and here is a bond, and here it is our N. Here again will become double bond. Here it is O minus positive charge, and in the last step, this pair of electron will be shifted to here. This bond is going back. Now you can see that in the third structure, 1, 2, 3. In the third structure, you can see that the negative charge is from the ring. The negative charge from the ring is coming out. So the negative charge, you can see that NO2 group attached carbon is carrying a negative charge. NO2 group attached carbon is carrying a negative charge. Okay, so that negative charge will be pulled out, and which will decrease the electron density on the nitrogen atom. It will completely decrease the electron density on the nitrogen atom, because here you can see that this NO2 group attached carbon, this carbon is having a negative charge and electron pair. This NO2 group, you can see that this is pulling out this electron pair out of the ring. That means it will reduce the entire electron density on the ring, or and hence it will reduce the negative charge on the nitrogen atom, because the NO2 group is attached carbon is carrying a negative charge. That negative charge is coming out. Clear? In the case of, so there is a here you can see that there is a decrease in the negative charge on the ring and negative charge on the nitrogen atom. But this case will not happen if the NO2 group is at the meta position. So look at it here. Look at it here. If the NO2 group is at the meta position, what is happening? NH2, and here it is NO2. Okay, NO2 means okay, NO2. Now look at here. Okay, this is coming here, and what will happen? Then this will come here. Okay, so you get a structure like this, double bond NH2 plus, and here is a pair of electron, and here it is like this. Here it is N. Okay, double bond O minus plus. Next step, this will come here, and this will go here. Okay, you get a structure like this. Here it is like this, double bond NH2. Here it is plus. Okay, here it is N, double bond O minus plus. Here is a pair of electron. Okay, it is like this. And in the next stage, you can see that this pair of electron is shifting to here. Clear? And what is happening? This bond is shifting to here. Okay, that means you get a structure like this. Okay, here it is double bond NH2 plus, which is a pair of electron, and here is a double bond, and here it is NO2 only. So you can see that here NO2 attached carbon is not getting a negative charge, therefore the NO2 will not pull out the negative charge from the ring. Okay, that means when the NO2 group is attached to para position, it will pull out the electron density, which will reduce the electron density on the nitrogen atom, therefore which is less basic than when the NO2 group is at the meta position. Okay, when it is at the meta position, it attached carbon, NO2 attached carbon is not getting a negative charge, so it will not pull out the negative charge electron density from the ring. Okay. Okay, that's all about the basicity of aromatic amines, and thank you.